Hi, I'm Ben.
I'm Alazar.
And I'm Thomas. And we're Group 5. This is our ECE 4534 Rover. And we're going to explain to you how we made this rover to take an area of an enclosure. And, yeah. So we have our infrared sensors here. These are for short range distance measurements. It goes from about 3 centimeters to 30 centimeters. These are really cheap. That's like the major benefit to them, but they're analog sensors, so they aren't as accurate as our laser sensor, which is right here. And this was a very, very expensive sensor. This one cost about $99, and it was kind of an experimental. None of the other groups in our class used a laser sensor, and this is kind of like, as far as embedded systems, this class in general, no one had really used one before. So basically, it actually ended up being extremely accurate, and it worked way better than infrared sensors for taking reliable distance measurements. I mean, only the major downside of the sensor is it has a really, really slow duty cycle. So that means basically we could only get a distance measurement once a second, which is, compared to these infrared sensors, you can sample them much, much, much faster. And the last sensor we have on this rover is our compass. This is another pretty cheap sensor. It only costs about $30, I2C. We were going to use the sensor in conjunction with the laser to take a distance measurement from the laser and then pair it with a heading measurement from this compass. And so basically we figured if we had these two data points with the infrareds as a backup, we could essentially take the area of any enclosure, because as long as you have a distance and then an angle between, you can make triangles. And I'll get more into the algorithm stuff, but we figured that these sensors would be accurate enough to help us with that goal. Ultimately, the compass turned out to be pretty inaccurate. The error on the data sheet said it would be around 2.5 degrees plus minus, and that seemed decent, but in real life it wasn't that accurate, especially inside in a room with lots of magnetic interference. So this actually produced a lot of error in our calculations. So going back, we probably would not have used this, but we did. So basically, the rover is made up of 3 picks and these sensors and a motor controller, and Thomas will talk more about the motor controller. But essentially how the flow of the rover works is there's a timer interrupt on this master pick. The master pick talks to 2 other picks. And so when this timer interrupts, it tells the slave pick to send the sensor data to the master pick. So the timer interrupts 6 times a second, and then the slave responds 6 times a second with 3 infrared sensors, 1 laser sensor, and the compass also responds on an I2C bus. So immediately once we receive all that data, this master pick sends all that data to the arm through UART interface, and Thomas will talk more about the other pick, which is the motor pick.
So here we have our rover as constructed. We have our infrared for detecting size over here, the short range infrared sensor. This is our master pick. It's attached to the top, and that is attached to the compass, which is not here anymore, but the compass is up here. This is battery pack, which I'm going to remove, and then Wi-Fi for wireless communication. So if I take this off, here we have the inner layer of our rover, and these cables lead to the analog infrared sensors. This is the slave pick in charge of gathering sensor data. This is the motor pick, which sends controls to the motor controller, the saber-tooth motor controller at 19200 baud, and all of these All of these 3 picks are connected through I2C communication, which is this cable. If I take this off, you can see the inner workings. So this is what controls our motors. This here is the saber-tooth motor controller. It is actually, in addition to controlling the motors, it provides the power to every component on the Rover side. So it is especially important for us to have a good common ground and a distributed power system. We actually have all of these boards running in parallel power, splitting off of the motor controller. These are the motors, and these are actually rotary encoders for the motors, which we are not using. I'll get into that a little bit later. So as for how I control the motors, the saber-tooth motor controller is run in simplified serial mode, which basically means that I send it 2 byte commands. One byte command will control one side of the wheels, and the other byte command will control the other side of the wheels. The byte command ranges from 0 to 255, with 0 to 128 as controlling one side, and then the rest of the numbers control the other side. So in order to implement these, ideally you would want the motors to run at the exact same speeds. And this can get kind of complicated, basically due to differences in manufacturing with the motors and for output. When the batteries get low, the motor controller actually outputs less amperage to the motors, and this will cause the motors to move slower, and it can get unsynchronized very, very quickly. One of the things I did to resolve this problem was very simply just keep the battery charged at all times, no matter what. We were given 2 battery packs, and we switched them and kept them on charge every 10 minutes or so, 10-20 minutes. As for controlling the actual wheels, I decided, in addition to tweaking, to implement a system where the first wheel that moves at regular speed, but then the second set of wheels that moves actually moves at a faster rate compared to its normal speed, the speed that you want it to run at. This is due to the fact that the motors actually start up at different times. So one side will start before the next. In order to catch up the lost distance, to offset it, you would have to run the second set of motors a little bit quicker, just for the first split second in order for it to catch up. This actually helped, and it made our drift amount less than ½ an inch, which is pretty acceptable.
So basically, I designed the area algorithm to calculate the area of an enclosure. First approach was to do a 360-degree scan of the environment, and based on that scan, approximate the area. The second approach was to follow along the walls of the enclosure and calculate the area from that. To do the 360-degree scan area calculation, the method I used was to get 3 readings from one side. So I would consider the first 2 points I get to get the line of the side, and then to conclude that that was indeed a side, I would take the 30 points, plug it into the equation I got plug into the equation I got from the first 2 points, and if it is within a margin of error of where it should be, I would conclude that I have a side established. And I use this method to establish the equations for all sides. Once I have all my equations calculated, I would find the intersections between any 2 lines. So that would give me my corner points between the sides. And then once I have these corner points, I would just make triangles from the center and calculate the area of each triangle. That would give me the area of the enclosure. In simulation, this turned out to be very accurate. However, our compass data was not very reliable, so a lot of the points actually ended up not counting as part of the site, and we weren't really able to get very accurate results for the area calculation. And the second approach is very similar to the first one, except this one, what I do on this one is I would consider myself to be somewhere in the positive x-axis, and then from here I would get the distance to the closest corner, and then I would save this location, and then I would go to this location and get the distance to the next one, and I would save both the angle and the distance I have to this corner point, right here. And just following that, I would just get the coordinates of each corner point, and then make out triangles and calculate the area. We weren't really able to get very accurate results for this one either, because our compass data was very unreliable, and that kind of brought down the entire thing. So the design behind the navigation for the rover was pretty much a state machine. The rover had 5 states. It was initial 360-degree scan, a state to go to the nearest wall that's in front of the rover, a state to follow along the sides of the rover, a state to make a turn when there is something blocking the path of the rover, and the final state to stop. Basically, the rover decides in which direction or what kind of action, what kind of motion to perform based on the sensor readings. Once it has the sensor readings, and in conjunction with the compass, or rather with the current state it's in, it decides what kind of action the rover needs to take. And the navigation worked out pretty well. We were able to navigate enclosures without hitting too many walls, and it turned out very accurate.
Here is our rover performing a 360-degree turn to calculate the area of an enclosure using the algorithm Elazar mentioned earlier. In this particular case, the enclosure is an octagon. The calculated area of this run is 16 feet squared. The real area was roughly 19 feet squared. As mentioned earlier, probably the greatest source of error we had was from the compass. Since we took so many angle measurements in this run, the errors add up and the result is somewhat far off. At the end of this run, you will be able to see that the rover does not actually end up in the exact same place from which it started in the beginning. A possible solution we could have used was to implement the rotary encoders. This would allow us to measure the distance traveled by each wheel and confirm how much the rover is actually rotating. This would also allow us to confirm and generate much more accurate angle measurements. Along with an improved algorithm, we would be able to generate much more accurate area measurements.